Although electric cars are recognized for their speed, the Tesla Plaid is the fastest production car ever to accelerate. A number of variables contribute to this, but the three unique electric motors in the battery pack are what really make the Plaid what it is. The innovative designs of Tesla's electric motors are worth investigating further. But before we do so, please make sure to subscribe to our channel and give this video a high five. If you've ever used a compass, you know that the needle always points north, aligning with the Earth's magnetic field. If you bring a magnet close to the compass, the needle spins to align with the magnet, creating the strongest force of attraction. On the other hand, a magnet can produce a strong push or propulsion. An electric motor uses the strength of push and pull to spin itself, but consistent rotation requires electromagnets. Compass the needle will continue to spin. This is an example of induced rotation utilizing a magnet. A permanent magnet, such as the one on your fridge, has a physical north and south pole that cannot be changed. But the magnetic field of an electromagnet follows the direction of the electrons moving through the conductive material. Although there is a lot of high-level engineering involved, understanding the fundamentals of Tesla's electric motors is not too difficult. Copper is an extremely conductive material that is not magnetic. However, when an electric current flows through it, it becomes an electromagnet, giving us incredible control over the magnetic field. The design of Tesla's induction motor is based on Nikola Tesla's invention, and the motor's operation depends heavily on electromagnets. By conducting electricity through conductive materials, we can harness the power of magnets to create rotation, which enables electric cars like the Tesla Model S to accelerate the reversal of electricity flow and the reversal of the magnet's poles. This means that depending on the type of juice you give them, electromagnets can swing both ways, and you don't have to physically turn the magnet inside the electric motor to reverse its poles. The rotor and stator. The rotor is the inner center of the motor, while the stator is its outside ring spinning the stator station area. While the rotor is rotated in this application, the rotor is an iron core surrounded by rows of permanent magnets that run lengthwise. And for simplicity, let's say there are 4 rows evenly spaced around the ring top, bottom, left, and right. Each quarter of the ring has an alternating pole, so they go north-south as you go around. The stator is a tube of electromagnets made up of many coils of copper wire that surround the entire ring, also running lengthwise. Each coil of wire is an individual electromagnet, and each one can be turned on and off and have its polarity flipped just by controlling the flow of electricity into each coil. By placing the rotor inside the stator, there's a magnet within a magnet, a permanent magnet inside an electromagnet. Anytime you put 2 magnets near each other, there will be a natural push and pull, and the opposite poles will pull towards each other while the poles will push away. But once the initial alignment is complete, the rotation will stop. To maintain that rotation, all you have to do is constantly move the north and south poles of the stator magnets around the outer ring, and again you do that by controlling the direction of the electrons flowing through the coil of wire. By moving the south pole of the stator around in a circle, it'll pull the north pole of the rotor along with it, and conversely at the same time, the south pole of the stator will push the south pole of the rotor as it moves around that ring. That constant force of push and pull will spin the rotor. And when you see the Tesla T logo, a cross-section of an electric motor, the rotor will spin faster the faster you move the magnetic field surrounding the stator. Hopefully, this explanation made sense and was largely true. The top curving line represents the stator ring, and the pointed T shape represents a slice of the rotor. It might not be suitable for a textbook, but it ought to be sufficient to convey the essential idea. The next thing Sandy Munro discovered while disassembling the Model S Plaid was about the bearings. Standard ball bearings were used in earlier Tesla Motors models to enable the rotor to spin smoothly inside the stator. But in the Plaid motor, Tesla upgraded to ceramic bearings, which have a few advantages over steel bearings, including lower friction, higher durability, and the capacity to operate at higher temperatures. Finally, Sandy Munro discovered that the Plaid motor uses a new type of insulation material. In previous Tesla motors, the insulation was made from a material called Nomex, which is frequently used in the aerospace industry. However, in the Plaid motor, Tesla has switched to a new automated process for winding the wire, which allows for faster and more precise winding and can help to improve the performance and efficiency of the motor. This is an interesting discovery Sandy Munro made regarding the wiring inside the Plaid motor. Peak polyester ether ketone is the replacement substance that Tesla is using instead. PEEK is a high-performance plastic with exceptional chemical and thermal resistance. making it perfect for use in high-temperature applications like electric motors. According to a recent article, Tesla has made efficiency a top priority in their manufacturing processes. This is demonstrated by the fact that every automobile uses the same basic part and doesn't waste time modifying the board's printing, because they all just state Model 3. The single modification for the Plaid inverter board is actually an explosive fuse that acts as a tiny bomb, firing two pushers straight out that physically break two of the bus connectors that link the power from the inverter to the motor. This ensures that the motors go completely dead in an instant if something catastrophic happens to a Model S Plaid, though it's unclear what would cause this fuse to fire. Additionally, all three motors in a Plaid vehicle are exactly the same, making it the most efficient choice for production. Tesla even invented an inverter for the Model 3 that they liked so much that they implemented it into every motor in their lineup. The report's author, Sandy, discusses the benefits of having two motors in the back. Using one motor per wheel results in greater simplicity and more power. Using a single motor to drive two wheels instead of a differential or other object between the motor and the wheel increases the possibility of energy loss due to friction or the gear set. As a result, the only object between the Plaid due to the fact that Tesla lacks a transmission and only has one fixed gear ratio, a single gearbox connecting the motors and the back wheels is essential. Interestingly, the Plaid motor stator is exactly the same as the one found in the Model 3 NY motors, optimizing production efficiency. However, the rotor has undergone major modification. Although the hosts were a little perplexed by it, Sandy and his crew had never seen a design like this inside an electric motor. Tesla uses car-shaped laminate sheets to create the iron core of the rotor, with 529 of these stars making up the core and creating 6 rows of magnets around the rotor. The magnets are then capped off by another laminated piece that looks exactly like the Tesla T logo. These caps don't connect to the core of the rotor and are just held on by the magnets themselves. According to Tesla, the floating caps and laminated star construction result in a 25% boost in power and torque capacity. To test the Plaid motor, note that its permanent magnets are also substantially more potent than those of a normal electric car motor, such as Tesla's standard motor. When measuring the force necessary to remove a bolt from the rotor magnets of different models of electric cars, Monroe and an unconfirmed source discovered that the Plaid required 151 newtons of force, while the Model Y required 112 newtons. While the Mustang Mach-E needed just 81 newtons, the BMW i3 needed 93 newtons. This suggests that the magnets in the Plaid rotor are more than a third more powerful than those in the Model Y and Model 3, and nearly twice as strong as those in the rotors of the Mustang Mach-E. Despite the complexity of the subjects, acquiring knowledge about the technologies and capabilities of the plant can improve the experience of driving an electric vehicle. Lastly, they express their gratitude to the Patreon supporters for helping them create high-quality content, which pretty much sums up this video. Thank you for watching, and don't forget to give this video a big thumbs up. Enthusiastically, the host encouraged viewers to share their thoughts in the video, and to let them know if any information was incorrect. I'll see you in the next one.